Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing moving charge on magnetism. In just previous lecture, we have discussed magnetic field due to a straight current carrying conductor or wire. And of course, we have discussed how to find magnetic field at the center of the circular coil carrying current. And we have discussed how to find magnetic field at the center of an arc, means part of a circle carrying current. And in this lecture, we will discuss another application of Biot-Savart law, that is magnetic field intensity or magnetic field at any point on the axis of circular current carrying coil or current carrying wire. Magnetic field at any point on the axis of circular current carrying wire. Okay. So before going to discussion, let's again recall Biot-Savart's law. This is a conductor of any shape. dl is elemental length, and magnetic field we have to find at P due to this elemental length of conductor carrying current. Okay. So angle between dl and r is position vector of point P with respect to dl. Angle between dl and r, direction of dl is taken along the direction of current, and this is position vector. Angle between dl and r is theta. Then magnitude of magnetic field in accordance with Biot-Savart law is given by mu 0 by 4 pi I by r square into dl sin theta, and this is vector form of Biot-Savart's law. Mu 0 by 4 pi into I by r cube into dl cross r. Okay. Then what is direction of dB? Direction of dB is along the direction of dl and r, means cross product of dl and r. So direction of magnetic field can be calculated or can be determined by determining direction of dl cross r. So the direction of magnetic field is same as that of direction of dl and r. And you know, suppose this is a vector, this is a vector, this is b vector. Okay. Any direction you may take, this is a vector, this is b vector, and angle between them is theta. A and b are taken on xy plane. A vector and b vector are on xy plane. So direction of A cross B, result of A cross B is C vector. Okay, A cross B is equal to C. Then what is direction of C vector? Means direction of A vector cross B vector. Then A vector cross B vector, if you apply right hand thumb rule, direction of A cross B is perpendicular to both A and B, means direction of A cross B is along z axis. A cross B outward or B cross A inwards. So whatever may be, A cross B is outward direction or along z axis. So direction of cross product, A cross B is outward or B cross A is inward, whatever may be. Direction of cross product is perpendicular to both the vectors. Direction of A cross B is along z axis and it is perpendicular to both A and B. Since A and B are taken, we have taken on xy plane. So z axis is perpendicular to xy plane. So direction of cross product is perpendicular to both the vectors or perpendicular to the plane of the vectors. This is our basic concept from vector analysis. Okay. Then direction of dB is along the direction of dl cross r. Okay. So direction of dl cross r same as that of direction of dB. Okay. Then application of Biot-Savart's law to get magnetic field intensity at any point on the axis of circular current carrying wire. Okay. Let's take a circular current carrying wire. Oh, this not looks as a circle, no? Okay. This is the circular current carrying coil. Suppose current is flowing in anti-clockwise order. Then what you decide? The plane of circle. This is plane of circular coil. Plane of circular coil is parallel to the plane of this white board. The circle is like this. The plane of circular conductor is parallel to this board. If this board is taken, white board, on XY plane, then plane of this circular coil is parallel to XY plane. See, this is Z axis. If this circle is taken on YZ plane, this is YZ plane. This circle is taken on YZ plane, means the plane of circle in this case is perpendicular to XY, means perpendicular to plane of XY. So here I have taken the circle like this, means plane of circle is perpendicular to plane of this white board. This is the diagram of a circle. Plane of circle is parallel to this white board, and this diagram represents plane of circle perpendicular to the plane of this white board. Clear? Okay. Let this coil is carrying current I. I have taken in anti-clockwise order. You may take in clockwise or anti-clockwise, whatever may be. Okay. This is axis of coil. Axis means a straight line passing through center of circle and perpendicular to plane. If this is circle, then this is axis. Axis is perpendicular to plane of the circle and passing through center. Passing through center and perpendicular to plane of circle. Okay. We have to find magnetic field at any point on the axis. Let's consider this is point P on the axis. Okay. And White-Savart law gives an empirical formula of magnetic field due to an elemental length of conductor. We can't find magnetic field at point P due to whole length of circular coil. But we can determine total magnetic field. But first we have to get dB. Means dB is magnetic field due to an elemental length of conductor. This is whole circular coil. Okay, let radius of the circular coil is A. Radius of circular coil is A. This is also A. Okay, let's consider an elemental length dl at any section. Here, any point. So I have taken an elemental length dl on the circular coil. Then what is direction of dl? Direction of dl is taken along the direction of current. Here current is flowing in anti-clockwise order. Okay. So we will take direction of dl, but this is position vector of point P. This is point P. Position vector of point P with respect to dl, and position vector is R. This is dl, this is R. Okay. Then what is direction of dl? Determine first direction of dl. Direction of dl is taken along the direction of current. See, current is in anti-clockwise order. Okay. Means in a curved path. Then to know direction at any point, we have to draw a tangent. See, this is anti-clockwise order. At the top of the circular coil, at this point, if current is anti-clockwise, then this is the direction of dl. If the circle is taken like this, means the plane of the circle is parallel to this white board, and this is dl, then direction of dl is along the tangent. But here the circle is not kept parallel to this plane, but perpendicular to this plane. This is the circle, and current flowing in anti-clockwise order. So at the top part dl, direction of dl is along the tangent. See, Current anticlockwise, current is flowing in anticlockwise order. Current is flowing in anticlockwise order, and this is DL. Direction of DL is along the tangent. Okay, means inwards. Direction of DL is inwards. Okay, let's take this is direction of DL. Direction of DL. This part is DL. Direction of DL is inwards. I have shown like this. Direction of DL is inwards. Okay. Then direction of DB is perpendicular to the plane of DL and R, means perpendicular to both DL and R. So direction of DB is determined by taking or by deciding or by determining the direction of DL cross R. See, current is flowing in anticlockwise order, and this is DL. DL is inwards. This is R. DL is inwards, and this is direction of R. See, DL is inwards. This is DL inwards. This is DL. This is arrow mark. This is DL, and this is R. This is direction of R. R is inclined, not horizontal. R. This is R. DL is inwards, and this is R. Then what is angle between DL and R? You just see. Angle is 90 degree. Angle is 90 degree. This is DL and this is R. Angle is 90 degree. Just see. This is direction of DL and this is direction of R. Okay. So angle is 90 degree. Is it clear? So angle between DL and R is theta. Theta is 90 degree. Okay. Then what is direction of DB? Means magnetic field at point P. Direction of DB is along DL cross R. DL is inwards. DL is inwards like this. This is DL and this is R. DL cross R. DL is inwards and R is perpendicular to DL. So DL cross R. DL cross R. So direction is like this. DL cross R. This is DL inwards and this is R. So DL cross R, you just imagine three-dimensional view. This is DL, direction of DL, and this is R. This is R. DL cross R. DL cross R. This is DL. This is R. You see like this, it will be easier. This is direction of DL. This is R. DL cross R. This is the direction. Okay. So this is the direction of DB. Perpendicular to the plane of DL and R. This is the plane of DL and R. The plane is like this. This is the plane of DL and R. DL inwards and R is inclined. This is plane of DL and R, and direction of DB is perpendicular to plane of DL and R. Okay. Do you understand? This is DL inwards, this is R. DL cross R, DL cross R, this is R. DL cross R, this is DL. Okay. So DB is perpendicular to both DL and R. If this is DL, this is DB, perpendicular to DL. If this is R, DB is perpendicular to R, then perpendicular to both DL and R. Okay. Let this angle is theta or phi. Theta is taken 90 degree. This angle is phi. Okay. Then similarly, the whole circular loop may be considered to consist of a number of elemental sections, each of DL, 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 and so on. Okay. Just take another elemental length just opposite to this DL. This is also DL. So current is flowing in anticlockwise order. Current is flowing in anticlockwise order. You see, current is flowing in anticlockwise order. Then at this point, direction of DL, if current is anticlockwise, then this is the tangent, means outward. At top, This is the coil. Current is flowing in anticlockwise order. At top, direction is inward, and at bottom means here direction of DL. Current is flowing like this, and this is the tangent means outward. Okay. Then this is direction of DL. Again take position vector R. It looks like this, but not actually like this. This is the outward direction. An angle between DL and R again 90 degree. Theta is 90 degree. And here direction of DB, due to this elemental section DL, direction of DB may be taken like this. Cross product of DL and R. See, DL is outward, DL is outward, and R is inclined. So DL, this is DL towards R. This is DL. See, this is DL, this is R. DL cross R. This is DL, this is R. DL cross R. Again this direction. So this is direction of DB. Just think three-dimensional view. Here DL is inwards and here DL is outwards. DL cross R, direction is perpendicular to DL and R, means perpendicular to the plane of DL and R. Okay. Again this angle is phi. This angle is phi. So draw a line perpendicular to axis. See. This point P. This is DB. Draw a line perpendicular to axis. Okay. See, what is this angle? This angle is phi. Okay, you just make this one. It will be easier. This angle is phi, this angle is 90. Then what is this angle? 180 degree. The total angle is 180 degree. 180 degree minus 90 plus phi. This is phi, this is 90. Rest angle is 180, 90 minus phi. Means this is 90 minus phi. So this angle is 90 minus pi. So what about this angle? The total angle, this angle is 90 degree. So 90 degree minus 90 minus pi. So it comes pi. So this angle is pi. Similarly, this angle is also pi. Is it clear? This angle pi, this angle 90. So rest of angle is 90 minus pi. This angle is 90 minus pi. This total angle is 90. So this angle is 90 minus 90 minus pi is pi. Now resolution of vector dB. Component of dB along this direction dB cos phi, and along this direction this is dB sin phi, and in accordance with the similar way, direction of dB means component of dB along this direction is dB cos phi, and again along this direction is dB sin phi. So as we have discussed, the whole circular coil may be considered to consist of a number of elemental sections each of dl. Okay. So dB cos theta, where should be dB cos theta? dB cos theta, 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 and dB cos theta. See, in space here, imagine YZ plane. This is x-axis, and this is y-axis, and this is z-axis. Imagine YZ plane. On YZ plane, how dB cos theta, cos phi is distributed. This is on YZ plane. Y-axis, z-axis. This is on XY plane. The coil is on YZ plane. Okay. So this is dB cos phi. This is also dB cos phi. This is 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 dB cos phi. So sum of all these dB cos phi is 0. So you may take here. This is sum of dB cos phi. This is also sum of dB cos phi, which cancel each other. Which cancel each other because it is symmetric and in opposite direction. So the sum of dB cos phi is 0. Both cancel each other. Magnetic field is vector. So dB cos phi, sum of dB cos phi, sum of dB cos phi cancel each other. Okay. Then resultant magnetic field is only this component, means sum of dB sin phi along this direction. Sum of dB sin phi. Then sum of dB magnitude, we are taking magnitude sin phi. Then B is equal to, we may write sum means integration of dB sin phi. Then integration of dB, formula for dB, magnitude of dB, mu 0 by 4 pi I dl sin theta. Here theta is 90 degree. Here theta is 90 degree. Ideal sin theta divided by r square. Then in place of dB, I can write mu naught by 4 pi I dl by r square into sin phi. Because sin 90 is 1. Mu naught by 4 pi I dl by r square. Okay. Then B is equal to mu naught I divided by 4 pi r square integration of dl into sin phi. What is sin phi? See, let this distance is x, means from center to point P is, let's take x. This angle is 90 degree. Then this is phi. Sin phi is perpendicular upon hypotenuse a by r. Then B is equal to mu naught I a divided by 4 pi r cube integration of dl. Integration of dl. See, we have taken elemental length dl. Radius of the circle is a. Then whole length of circular conductor, means limit varies from 0 to 2 pi a. If the coil contains n number of turns, then we may multiply n. We may multiply n. If the coil contains n number of turns, then B is equal to mu naught I divided by 4 pi r cube into integration of dl is L. Limit varies from 0 to 2 pi a. Then B is equal to mu naught I divided by 4 pi r cube into 2 pi a m minus 0 pi. And this is 2. B is equal to mu naught n I a square divided by 4. This is 2 r cube. Okay. Then from this right angle triangle, base is x, perpendicular is a, hypotenuse is r, then r is equals to square root of x square plus a square, or r is equal to x square plus a square to the power 1 by 2. Then putting this value here, expression of r, magnetic field, magnitude of magnetic field, mu naught ni a square divided by 2r cube, 2 in place of r, x square plus r a square to the power 1 by 2, but power is already given 3, means whole to the power 3 by 2. This is your expression for magnitude of magnetic field. Then what about direction? See, direction of magnetic field is along the direction of sum of dB sin phi. This is sum of dB sin phi, means direction of B, if current is flowing in anticlockwise order, direction of B outward. Okay, means along positive x axis, on both sides, this side also, direction will be same. Y direction will vary. We have already discussed in from very beginning class. Okay. Suppose see, current is flowing in anti-clockwise order. Then this is direction of magnetic field. This is south pole. This is north pole. Direction will be same. Direction will not differ. This is direction of magnetic field. Or you may consider again. To clarify this, you may consider here another point P and position vector is also R and R. Okay. Then here, what is direction of D? Direction of D. Direction of D due to both elemental parts, and this is sum of, this is phi, this is phi, this is dB cos phi, dB is cos phi, and this is dB sin phi. Again, sum of dB sin phi perpendicular to plane, and it is along positive x-axis what we have taken for anti-clockwise flow of current. Similarly, you can decide the direction of magnetic field. This is direction of B. Direction of B. If current is in clockwise order, if current is in clockwise order, also you can represent. I am erasing this part. You have got your final result and showing you how to determine direction in clockwise order. Okay. Suppose this is a circular coil. Current in clockwise order, I. Then this is DA. This is A. This distance is R. This is point P. This is R. Then in this case, what is direction of DLC? Current is flowing in clockwise order. See. Current is flowing in clockwise order like this. Current is flowing in clockwise order like this. In direction of DL is outward. Current is clockwise, direction of DL is outward. Direction of DL is outward. This is direction of DL. This is R, again it is perpendicular. This is direction of DL, this is R, angle is 90 degree. Then DL cross R, see, DL is outward, R, DL is outward, this is and this is R. DL cross R like this means this one direction of magnetic field DB. Similarly, here we take DL, this is R, and here magnetic field is like this. Then again the similar pattern on this side or on this side. Okay, fine. Then this is expression for magnetic field at any point, means at any distance x. Here x is variable. X is variable at any point P. X is distance from center of the coil to point P. X is variable. Radius is constant. A is constant. Current is constant. And n is number of turns. You may put 1. So, value of magnetic field, magnitude of magnetic field depends upon x. If x is minimum, then B is maximum. So x is minimum when x is 0, means at center of the circle. See, from center to point P is distance x. If x is 0, then point P will come to center. Oh, you got center of the circular coil. In just previous lecture we have discussed, if current is I, radius of the circle is R, then magnetic field at the center, mu 0 I by 2R. If number of turn is n, then you may take mu 0 and I by 2R. Then what it comes? Magnitude of magnetic field, mu naught Ni A square divided by 2. X is 0, then A square to the power 3 by 2 means A cube. Then magnitude of magnetic field is mu naught Ni by 2A. Here radius is R, here radius is A. So this is magnetic field at the center of circular coil, and this is maximum. At center magnetic field is maximum. If X is infinity means maximum. If X is maximum, then B is minimum. Then what is minimum value of magnetic field on the axis? Means at infinity. If X is infinity, then magnetic field is 0. If X is infinity, then all is infinity, then magnetic field is 0. Means magnetic field is 0 at infinity and magnetic field is maximum at the center of the circular coil. Okay. Then the related graph. I may do here. Okay. Let variation of magnetic field is shown along y-axis. This is center, means here x is 0, this is along x-axis. Here x is 0 at center, and at center magnetic field, this is y-axis. At center magnetic field is this much, mu naught Ni by 2 at center. And magnetic field is 0 at infinity, means as distance increases, magnetic field goes on decreasing and becomes 0 at infinity on either side. Okay. This is variation of magnitude of magnetic field with distance at center. X is 0 and x tends to infinity, magnetic field tends to 0. A by 2. From mathematical expression you can get it also. Okay. Here x is 0, this is x-axis. Okay. This distance a by 2. This distance is also a by 2, half the radius. Okay. So magnetic field decreases as distance increases and finally becomes 0 at infinity. And direct form numericals you will face on the basis of this theory. Direct form numerical. Okay. Suppose it is given like this. See. This is a circular coil carrying current I. This distance is x. Okay. This is also a circular coil carrying current I, and this distance is also x. Then what is magnitude of magnetic field at this point? We know direction of magnetic field is perpendicular to the plane of coil, and here magnetic field, this is in anticlockwise order, this is also anticlockwise order. So this is direction of magnetic field B. This is also direction of magnetic field B. Okay. Then angle between them is 90 degree. Okay. Then resultant magnetic field is root 2 B. Simple question. If radius is A, then the resulting magnetic field is root 2B, means this is equals to root into mu naught a square divided by 2 into x square plus a square to the power 3 by 2. All these factors are same. So these are simple questions on the basis of formula only. Thanks my children. Thanks.